this module, we will discuss what a link budget is, the importance of a balanced distributed antenna system, and how to calculate your system's expected noise factor to determine your BDA's uplink gain and ensure the radio network is protected. A link budget is simply a layout of your losses and gains from component to component throughout your ERCES. A report like the one seen here shows your total signal strength at each service antenna. This helps ensure your distributed antenna system, or DAS, has been connected properly and that the correct components are connected to the correct cables and antennas. These reports can reflect both uplink and downlink budgets. When designing a system, it is important to create balanced downlink power to each service or broadcast antenna. As you can see in this example, utilizing different couplers, tappers, and splitters allows you to keep the downlink power relatively even between all antennas in your distributed antenna system. The goal is to have a difference no greater than 6 decibels between all indoor service antennas. You can also use inline attenuators to help balance power when couplers, tappers, and splitters are insufficient. Balancing the system is important to prevent what is called the near-far effect. If antennas are too imbalanced, you may create an environment where the BDA will only connect the first responder under the strongest antenna, leaving the first responders further away unable to connect to the radio tower outside. As you see in this example of an unbalanced system, the first antenna is much stronger than the antennas further down the line, resulting in this near-far effect. Some components in an ERCES can reduce signal. This is called loss and can happen as the result of splitters, cable, dense interior materials, and a phenomenon called free space path loss. Reducing the amount of loss in the ERCES will result in increased signal to the antennas. However, loss can also be used as a tool to pinpoint coverage and help balance an ERCES. Free space path loss is the amount of loss a radio wave experiences as it travels through space. It is calculated through the formula here, but to give you some perspective, a radio signal leaving an indoor antenna will lose 50 dB of power at just 20 feet away. This is a significant amount of loss and should be considered when designing and optimizing an ERCES. When you install an ERCES, there is some signal that inherently bleeds out of the building. This is called signal leakage and should be minimal to prevent interfering with the signal provided by the donor site outside the building. The signal leakage from inside the building should be at least 15 decibels lower than the outside signal. To help achieve this reduction in signal leakage, consider installing antennas away from doorways and skylights. If designing an ERCES, it is crucial that you accurately account for interior walls and what they are made of. In the example here, you can see the same building and system layout. The left side shows signal propagation if the interior walls are drywall. As you can see on the right, configuring only the interior walls to concrete drastically reduces the coverage provided by the same design system. If using a design service, including accurate information will drastically improve system efficiency and ensure all critical areas are provided with adequate signal. As you can see from this table, different materials have different loss values. Even the weather and people can affect signal propagation and should be considered when conducting your site surveys. A major consideration in properly installing an ERCES is feedback, also known as oscillation. If indoor and donor antennas are installed too close together, they could create feedback, just like in an audio system. This feedback, if not resolved, could raise the noise floor at the donor site, causing the entire radio system to shut down, eliminating communications between all first responders. Take the necessary precautions and ensure antenna isolation before leaving the ERCES active for a prolonged period of time. Some steps can be taken to prevent oscillation. Set UL gain on the BDA to as low as possible and still meet the isolation requirements. Place the donor antenna on the edge of the building and point it away from the building so it doesn't see the inside antennas. Do not place inside antennas near windows, doors, or skylights. Do not use more bandwidth than is required by turning off unused bands. If oscillation continues, isolate the offending indoor antenna and install an inline attenuator to reduce its power. This is an excellent visual representation of the noise floor. The blue represents the amount of ambient noise created by electronics received at the tower. The tower allows a certain level of noise, but when an ERCES is not tuned correctly, it can raise this noise floor to dangerous levels, overtaking the signal it receives. The ratio between the RF signal and the noise floor is called the signal-to-noise floor ratio. The most devastating effect an ERCS can have is the amount of signal getting back to the donor site and causing it to shut down. This is caused on the uplink side of the BDA and must be prevented. Some AHJs may require -60 dBm at the donor antenna to help prevent this, so it is important to know if the AHJ has any requirements in place regarding uplink power. One way you can determine your uplink power is by checking your uplink power report provided by TowerIQ's design team. On the BDA, you are able to adjust the gain for uplink and downlink separately. If dip switches are not present, the adjustments can be made digitally via the Sentry graphic user interface. Free space path loss over longer distances can be seen in this table. An 800 MHz signal loses 95 decibels at 1 mile, 101 decibels at 2 miles, and so forth. This information will be important when determining your uplink budget and BDA uplink gain settings. Your uplink budget will help you determine how much gain your BDA needs to set to on the uplink. A simple link budget equation looks like this. Received power equals transmitted power plus gains minus losses. We are also able to compare the link budget to the noise floor from the start, which is what we will walk through now. To do this noise floor math, there is certain information that you will need. 1. You'll need to attain from the FCC licensee the current noise floor of the tower you will be transmitting to. 2. You will need your current BDA setting. 3. The BDA noise figure. 4. The donor antenna gain. And 5. The free space path loss from the ERCS donor antenna to the donor radio tower. Once you have these numbers, you will then add the noise floor to your current BDA setting, then add the BDA noise figure, add your antenna gain, and subtract the free space path loss from the ERCS donor antenna to the donor radio tower. We will now walk through an example. In the uplink budget here, the noise from the ERCS is -139 dBm and the noise floor is -134 dBm. Therefore, the ERCS will not raise the noise floor when operating at this gain level. If the noise floor is higher than the BDA noise, no attenuation is needed. Pause to review the math on your screen. In this example, with the donor radio tower much further away, we see that the power level getting to the donor site is much lower than the noise floor but may not have enough power to transmit usable signal. In this case, you should increase the gain by 10 dB or so. In this final example, we increase the starting gain of the BDA and propose a donor site only a quarter of a mile away. As you can see, the way this BDA is operating currently will add more noise to the radio network. This is unacceptable, and the BDA must have its gain reduced by either digital or physical attenuation. The difference between the noise floor and the uplink power coming from the BDA is 11 dBm, so the BDA should be attenuated by at least 11 decibels. Though a little extra gain reduction will ensure the BDA doesn't raise the noise floor due to unforeseen factors such as weather or radio tower gain adjustments. Thank you for watching the Link Budgets portion of Potter ERCES online certification program. If you have any questions concerning this module's content, or just want more information about our sales, design, or technical services, please don't hesitate to reach out.